Hello, everyone. Welcome back from a big summer break. I hope you guys enjoyed wherever you are. So we are very happy and excited to have Majid today with us from the Technical University of Munich. And he will be talking on optimal control and learning for contact-rich robotics. Just a short introduction about Majid. He's an assistant professor in the School of Information Computation Technology at TUM. He leads the chair of AI planning in dynamic environments and is also a member of the Munich Institute of Robotics and Machine Intelligence. Prior to joining TUM, he was a research scientist at the Empirical Inference Department at the Max Planck Institute for Intelligent Systems. Before that, he was a postdoctoral researcher in the Machines in Motion, a joint lab between NYU and Max Planck. Since the start of his PhD in 2012, he has been performing research on motion planning, control, and learning for legged robots, ranging from quadruped, lower limb exoskeleton, up to humanoid robots.
Thank you again for inviting me. Actually, I found your platform very cool and it's very interesting. So I'll try to join more actually in the future. And especially I would be interested to see more early career researchers, as you said, PhD, senior PhDs and early postdocs. I think it would be very nice to provide this platform for them. But today, I'm going to talk about optimal control and learning for contact-rich robotics. Mostly, I will talk about the few papers we submitted this year to humanoid. So it's a very, recent research. If you have any question in the middle of my talk, just feel free to just interrupt me. I'm not gonna watch the chat. So Ridaman, if you find some question, just interrupt me and ask, okay?
Yeah.
Okay, great. So a bit about myself and my research. Basically, I've been working on robotics now for, I don't know, maybe 13 years. So the start of my PhD, I started working on, there was a national humanoid robotics project in Iran where we developed a humanoid robot and we implemented some type of new motions on this robot and so on. So I was mostly doing basically motion planning and control on this robot, okay? But this is mostly classical methods like black box optimization and classical control. Since 2016, when I joined Max Planck, I started to work on more formal algorithms. So I started working on optimal control and mainly model predictive control. I worked on, basically, we also developed these kind of open source robots that actually was replicated by many researchers in the world. But the theoretical work I did mostly during my PhD was optimal control. But when I started my postdoc, I also started working more on machine learning and combining it with control theory. So this is a very, very quick introduction about my work. But the framework I use to basically perform control or decision-making for robotic systems is optimal control. And here I try in one slide to explain what I mean by optimal control and what I'm doing actually. So let's say we have a system that is basically written down by some differential equation that you can discretize. So this is the system. It can be any dynamical system ranging from I don't know, economic system to robotics to any system that is dynamic, which means that it evolves over time. So X is the state of the system, F is a nonlinear normally function, U is the control input or the actuation we put into the system, and W is the disturbances. So if we know X as the state of the system, basically we can use F to see what happens if we apply control input U to the system. But the thing is that normally we do not have access to X. We only can measure some basically some outputs of the system. For instance, for robotic system, normally we have force sensors, we have joint encoders, we have, I don't know, torque sensors and so on. And these do not give us the full information about the system. So what we can do is that we can use these observations to build a belief on the state of the system xk. So we can find pk, And this part is normally called a state estimation. So basically, we build a belief over a state of the system given the measurements. And finally, as a control engineer, we try to find a mapping between the belief state to the control action. Okay, and this loop continues until we, reach the goal that we want. So the main property, so optimal control basically builds on top of principle of optimality. And principle of optimality very simply says that if you want to optimally control a system, so from time 0 to any time to the future, the optimal policy or the optimal controller has this property such that any sub part of this optimal control sequence will be optimal for the sub part of the problem, right? So this is called principle of optimality. And simply it says that if you just break down a long sequence of actions and decisions into the future, if you basically find an optimal, if you have found the optimal sequence of actions for the whole basically time, these actions, the actions that you found is also optimal for this subproblem. So for instance, in this figure, it's very simple. So you found all the sequence of actions from U0 to UN minus 1. Now, basically, principle of optimality says that UK to UN minus 1 is also optimal for the tail subproblem from K to N. So why is this useful? The main reason is that now you can write down the optimization problem that is not optimizing over the whole sequence of actions into the future. But what you can do is that you can find something that is called value function, J. And if you know the optimal value function from the next step, xk plus 1, finding a control action UK that minimizes this cost functional, right, which is only a cost of the current action plus the value function, is enough to find a globally optimal, sequence of action. So this is very nice because basically it says that you can break down your problem to very, very small sub-problems and solve it. But there is a problem with this formulation, and this is what Richard Bellman called basically curse of dimensionality, which is this optimization problem doesn't scale well with the dimension of the problem. So for instance, if you have a point in the space, this point has 3 positions and 3 velocities, right? And if you only consider 10 possible values for this position and velocity, you will have something like 10 to the power of 6 possibilities. And this is only for decision-making of one point at one time step. Now, if you go from this point to a full humanoid robot with 100 states, you will have something like, if you only, again, consider 10 values, you will have 10 to the 100 possibilities. And this problem is intractable to solve, right? So this is the problem with naive use of principle of optimality or dynamic programming, also it's called. So normally, for most of the interesting problems or real-world problems, we need to basically find an approximation of this optimization. And there are 3 basically main components that we need to do approximation on. The first one is the minimization, the argmin operator. And since this optimization problem is normally continuous, to basically solve this, we cannot solve it in continuous time. So we discretize, and this is the first approximation we make. So pretty much always we solve optimal control in discrete time. And then this is an approximation. Because again, finding the continuous optimal control is most of the time intractable. The other thing is approximating expected value, because we have this W in this formulation, and W is noise. So it's a random process. Expected value averages over these costs, right? But finding the exact expected value is intractable. So we need to find some way to approximate that. And the third approximation, which is the most important one, is approximating the cost to go or value function. And if we have a good approximation of this J tilde, then pretty much it's easy to solve the optimal control problem. So the main difficulty in optimal control is to find optimal value function, right? So most of the algorithms are basically based on this idea. So now to find an approximation of this problem, 2 fields emerged independently, actually. The first one was optimal control that was developed by control engineers, and reinforcement learning that was mainly first developed by neuroscientists, actually. But at some point, people figured out actually they are solving absolutely the same problem. The only thing is that the way they solve it is a bit different. Normally, optimal control, you assume that you know physics of the system. So xk plus 1 equal to f and blah, blah. So you know exactly what this equation is, and you use the structure of this equation, you use the gradient of this function and so on. And what you do is that you predict into the future using this model and find a set of control sequence or control actions that minimizes this cost function, okay? In reinforcement learning, you take another approach. So what you do is that you do systematic trial and error. So you start with a policy that is normally, nowadays, it's mostly parameterized by a neural network. And then iteratively, you evaluate the value of this policy, and then you try to improve it over iterations. So reinforcement learning tries to basically tackle the problem through trial and error. Optimal control normally try to tackle the problem using iterative optimization. So you optimize the sequence, apply it, and then get the measurement, and then refine your control. Okay. But it's important to understand that actually they are solving exactly the same problem, because this is something that people normally do not appreciate. It's exactly the same optimization problem. The way you solve it normally, it's different. Especially nowadays, people do reinforcement learning in simulation because deep learning is difficult to do in real world because it's not sample efficient. And then when you do deep reinforcement learning, you are doing simulation as model of the physics. So you cannot say it's model free, it's already model based, right? So you are using the model. The only thing is that you are not using the gradients of this model or simulation. And basically, some people call reinforcement learning zero order optimization. Okay, so in my lab and in my research, basically we try to apply the theoretical, optimal control and reinforcement learning to different legged systems, humanoids, for locomotion and manipulation. My research agenda in the next few years, basically the idea is that we would like to build a humanoid robot and a control system such that when you give the robot a final goal, let's say clean the house or, I don't know, paint the wall, the robot figures out all intermediate decisions to achieve this. So we are still far from this point. That's why it's a research problem and we are trying to achieve this. My proposal to solve this problem consists of 3 different components. The first component is, I call it planning. I'm going to talk about it, what I mean by planning. Basically, you try to find a sequence of goals into the future and try to realize it. The second component I call it learning. Normally, doing planning all the time is very computationally inefficient in real time. So we try to learn some components of the planning such that we can run it in the real time. And finally, adaptation. By adaptation, I mean we need to have a robot that can adapt to new environments. So basically, we need to have a robot that can perceive the environment in real time and adapt it if something goes wrong. And I'm interested again in humanoid robots, but the thing is that it's very challenging, humanoid robot in general. So it's consists of basically locomotion and manipulation. To make it simpler, for now, mostly we treat them independently. So I work on locomotion of bipedal and quadrupedal and also on the manipulation. But my goal in general is to have an autonomous humanoid robot. Okay. So let's start with the planning. So what do I mean by planning? So in general, we have this. So this is the optimal control problem that normally we have. So we would like to minimize the cost function over a certain period of time, 0 to t. We have equations like x dot equal to f x on u. So this is a continuous, but normally we discretize. So it's going to be discrete at the end. And we have G, which is all constraints of the system, right? So you have torque constraint, you have, let's say, obstacle as constraint, you don't want to touch them. I don't know, all types of constraints. And you have initial and final condition as constraint to this problem, right? So this is the general optimal control problem. The main difficulty here for let's say, humanoid, for locomotion and manipulation, is that F is not a continuously differentiable, in general, model, right? So I here, when I wrote it down as an ODE, it's not very exact. Actually, you have a DAE. But let's assume that, we can write it like that. The problem is that when we have contact, when we have a system that switches its contact state, the system dynamics changes, right? And this is a absolutely and very, very difficult problem. So in mathematics, actually, it's called mathematical programs with complementarity constraints. And complementarity means that contact enforces this type of feature to the system that either you can exert force to the environment or you have a distance to the environment. And this is a switching behavior which renders this optimal control a hybrid optimal control problem. People have tried in the past to solve this problem holistically.
Anekdote erzählen, was sie vor kurzem mit einer Biene bei uns gemacht hat aus Stetzling.
Okay, I think it's not for me, the question. Yeah, we have this. So there are many people who tried actually to solve this problem holistically. And they have actually, there have been very nice, interesting works. For instance, the work of Yuval Tassa, they used Mujoko as simulation, which basically relaxes the equations of motion, the contact dynamics, and you can solve a continuous optimization problem, and so on. There is the work of Igor Murdoch, contact invariant optimization, the work of Michael Poza, it's called contact implicit, and so on. So people have tried to solve this problem holistically. But the thing is that, and also some of them made it work on the real hardware, but in general, they showed little success in practice, this approach of solving this optimization problem holistically. And nowadays, actually, the community has converged to this type of formulation, where what you do compared to the first formulation, we added two new decision variables to the system, S and A, right? And S and A are the discrete state and action of the system. So very simply, what here we define is that we define two-level problem. One is evolving over contact switch, S and A, and one is evolving over the normal time scale of applying torque and going to the next state. And by doing that, by augmenting the system states with S and A, now what we can do is that we can have two sets of constraints. One is the dynamics of the system, the first line, which is basically SKF as a function of SK minus 1 and AK. This is the evolution of the discrete state of the system, which says that, for instance, if you make a contact with the environment, you are taking this action, and then you switch the dynamics of the system. So you explicitly add the switching dynamics to the system. And now if you know the states of this discrete state of the system, which is which contact points are active, now the equations x dot, the second row of equations become continuous. What you do is that you can now explicitly write down the continuous dynamics and discrete dynamics. And now we have very good solvers to solve continuous and discrete optimization problems. And then we can go back and forth, or I don't know, sequentially with this optimization such that we can take the structure of the problem fully into account to solve this optimization. And this approach has been very successful in the past, let's say 5-6 years, both in locomotion and manipulation. And also we did a couple of work on that. But today I'm not going to explain that. I'm going a bit further. But to show you one step further, what is behind this optimal control problem, I want to a bit more go into the detail. So when we want to solve optimal control problem for a humanoid robot, there are three variables that we want to find the optimal trajectory for. One is the interaction forces shown by lambda, one is tau, and one is q. Tau is joint torques, and q are the joint trajectories. We have something like 50 degrees of freedom, and m number of interaction with the world can change depending on the state of the system. So as you see in this minimization problem, q, tau, and lambda are basically continuous decision variables, but also here I added something called n. And n is a binary switch. Depending on the end effectors being active in contact with the environment or not, n can vary between 0 and 1, right? So it's a discrete value, so it cannot have something like 0.5. Either the contact is active or not. And again, so we have a cost functional that minimizes, I don't know, the energy, the tracking error or something. The main equality constraint of this optimization problem is the equations of motions or dynamics of the system, or equations of physics. So these equations are highly non-convex, okay? Which means that there are multiplication of sine and cosine to each other. So it's a very non-convex optimization problem, which in practice makes it difficult for the normal off-the-shelf available optimization solvers to solve this. So this is the first difficulty. The second difficulty is that the humanoid robot or any mobile robot is under-actuated, which means that not all the joints of the system are actuated. For instance, base of the robot that is moving around is not directly actuated by any torque, right? It's only external forces that can actuate this degree of freedom. And finally, and most importantly, the system is hybrid, which means that, depending on the value n, if it's 0, it means that you do not have any force to the system, right? So for instance, if the robot doesn't have any contact with the board, the last term is fully 0, and the robot basically follows a projectile, trajectory. But now, depending on n, the equations of motion changes, which means that the system is a hybrid dynamical system. The equations of the equations of dynamics change depending on the state of the system. And now we have, so n is a binary variable, is one basically constraint. We have a joint limit, we have torque limit, we have force limit. So there are a lot of inequality constraints in the problem. And this makes it very difficult actually to solve this. First of all, because we have a mixed problem. So we have both decision variables that are binary and continuous. And solving mixed problems is much more difficult than solving either of the problem, either continuous or discrete. So this is the main difficulty, but also the problem is highly non-convex, very high dimensional. You have a lot of inequality constraints. So what we do, the first step to solve this problem is that we try to say, okay, let's assume some planner will give us this n, the binary variable, which says what is the contact sequence with the board. So if we know that, now we end up having only a continuous optimization problem, right? Now we can solve it. I mean, still it's a very difficult problem, but at least it's not a mixed problem. It's only a continuous optimization. So this is the first thing we do. And then after that, so if we have some search algorithm that can find n for us, we can basically solve the contact planning independently, or at least, in isolation. And this makes it, somehow the optimization problem much simpler. Okay. So solving the continuous problem in the past 5 years, we have developed multiple solvers that can be run in an MPC fashion on a real robot. So we could really generate a wide range of motions on the robot. So I'm not going to go through this today. Rather, I will talk about how to find this discrete, basically, optimization variable. So let's say somebody gives us this nonlinear model predictive control or the continuous optimization problem, right? So this, to some extent, we know how to solve it. But how to find n, or what's the sequence of n effectors going to contact, still is an open problem. And in this work, basically, this is a work that we submitted to Humanoid. We propose to use Monte Carlo tree search. So Monte Carlo tree search is a very simple search method. It's a probabilistic search method. And on the right, you can see how it works. There are 4 levels of basically 4 stages for this algorithm. Basically, it's a tree search first. So basically, you build a tree of the possible contact sequences into the future, and then you find with some iteration, you try to find the optimal one. So the selection stage, basically, you select one of the nodes of the tree. Expansion, you expand all these child nodes from this node. Then there is a simulation that you basically simulate randomly until a goal, for instance. And then there is a backpropagation phase where you backpropagate the result. So this is actually the algorithm behind AlphaGo, for instance. So they use so if you look at the game of chess, so chess, you only have discrete decision variables, right? So this is a efficient search method for let's say solving discrete optimal control problems. And here we use MCTS together with nonlinear MPC or continuous part of the dynamics as basically yeah, contact planner. And for instance, here, if you look at the video, so the robot wants to go from the red points to the green points, right? And the thing is that some of the, let's say, parts of the environment is not stable, right? So the robot should find some non-trivial set of intermediate contact location such that it can go basically to the end. And a normal naive planner that does not take that into account, this basically discreteness of the environment would fail to generate a successful motion. Okay. So MCTS is nice. Basically, we have shown, again, as I said, this is still an open problem in the community, how to find an optimal set of, let's say, patches to contact, for instance, in this scenario. But the problem is that while this is very efficient, still we are not able to do contact planning in real time, which means that here what we did was that it's basically we generate the plan and then we track the plan. But if something goes wrong, the robot is not able to replan basically its motion. And if you look at the time on the right figure, depending on the number of patches available in the environment, the solution time can even go up to 100 seconds. So it's really a huge optimization problem that we are solving. If we are lucky, we can solve it in, let's say, less than a second, but normally it takes more than that. But interesting is that this optimization can just find, so going from one location to the other, one initial pose to a final pose, the optimization, the MCTS can find multiple solutions to this problem. And for instance, in the bottom, you can see some of these solutions. So this is interesting because we have multiple solutions to the goal, and this can be helpful to generalize to general environment. I'm gonna tell you how we can use this property. Okay, so that's nice. Now how we know basically with these two components, which is MCTS and trajectory optimization, continuous optimal control, or nonlinear MPC here, we can generate automatically any type of motion on a legged robot, or also for manipulation. These are pretty much the same problems. So this is very nice. But now the problem is that, as I said, the computation is so high that we cannot run it in real time. So here we use machine learning to offload some of the computation to the offline phase. So in this work, we propose to use basically imitation learning to try to learn the solutions of MCTS, such that now we can run the policy as a feedback policy on the system. But there is a problem here. As I said in the previous basically slide, we have multiple solutions from one single starting point to a goal, right? And this basically, if you just simply use a normal neural network like MLP, what happens is that the MLP either just converges to one of the solutions, or it just averages between different solutions, which is disastrous actually. And also we tried another network, it's called pointer network. That's a different type of network, but still both of them fail to basically represent all the solutions of the system. But we figured out that diffusion models are very useful for this task because, when we have multiple solutions, it means that you have multimodal data set. And diffusions are perfectly suited for this kind of application when you have multiple solution, multimodal data set. And this helps us now to have a diffusion policy that can generate basically contact plan as a function of feedback. For instance, here in this figure, you can see that the robot can basically find different solutions from a starting point to the end point. And now here you can see that we are changing the goal in a reactive fashion, and the robot is finding a feasible path to go to the endpoint. And if it's not clear, actually some of these stepping stones are missing, so the robot cannot trivially go, from start to the end. Here is another scenario. So what happens here is that we randomly remove both the goal and also two of the stepping stones available on the path. And the robot, because it's a feedback system, it can basically replan and find a feasible plan quickly such that it goes to the next step. Okay, this is nice. We also showed in another work that actually we can cache more of the basically a computation to an offline phase. So here is again a bit refined version of the previous work. And you see that the environment is very limited and the robot is able to find a feasible path to go forward. Okay, so this is nice. So this is one way that we can use machine learning to combine it with optimal control or planning such that we can have a reactive contact planning policy. Now, if you see that the policy can run in real time, actually. Okay. But the thing is that also what we want to do is that, so now what we did is that we replaced the contact planner with the basically neural network. The other thing we want to do is that we want also to replace the MPC or the continuous solver with the network. And the reason is that if the robot is walking all the time, we do not want to replan all the time, right? MPC is solving an optimization problem in real time. And we want to basically cache the solutions to a neural network such that it's only inference happens in real time. And here what we did is that we proposed a new safe learning algorithm. I'm not going to go into detail, but the idea is that we use some type of imitation learning to find basically to replace the MPC controller with the basically neural network policy. And we tried different type of algorithms. We proposed some algorithm that is called loco safe dagger. So dagger is a standard imitation learning algorithm in the imitation learning community. And I'm not going to go into detail because yeah, it's a bit complicated. But the idea is that normally when you do dagger is that you start with the expert policy, you learn a function on top of that, you roll out. And then because the policy is not learned properly, you will have some errors. So you will have some distribution shift. And then you use the expert to relabel the mistakes you make such that at some point you basically master the task. And here what we did is that we proposed a safe, basically we use the safe version of Dagger to learn locomotion policies from MPC. And we have shown that if we use the safe version of Dagger that we proposed for locomotion, actually we can have a very little number of failures during training. And this is very useful. Why? Because if now, let's say, we have a robot working in the real world, right, with the MPC, but we do not want to replan all the time, right? We want to basically cache the solutions to a neural network. We can use safe daggers, which is basically minimizing the number of failures during training. And now you can basically learn the policy in the real world if you want. And here is one of the, for instance, scenarios. So the robot starts moving with the learn policy, but at some point it makes mistakes. It exits the safe region, and then the expert takes over, and then until it's back to the safe region and so on. And we have seen that actually local safe dagger that we proposed is able to basically recover also from different types of disturbances. Okay, so this is another way of using machine learning. And here is another work that we did recently. Basically, I'm not going to go so much into detail, but here is we worked a bit on how we represent the policy. So it's about representation of the input to the policy. So now if you want to learn multiple gates for locomotion, one simple way is that you learn different gates for different neural networks. But then you represent each gate with a name. Let's say on the left, you can say, yeah, 1 is for walking, 2 is for jumping, and so on. But we propose to do a better representation. We said that if we condition our policy on the contact switches, this better captures basically the shared structure between different locomotions, different gates. And with this, we could show that actually we can do better than state of the art. So if we condition on the contact, as you see on the right, the robot is better able to basically learn the locomotion policies. Again, I'm not going to go into detail. I'm just trying to introduce the general idea. So this is another work that we did to learn from the optimal control, okay? So we use optimal control as expert, and while learning, what we did is that we tried to condition on the contact, which showed a better performance, okay? So this is good. So I talked about optimal control or planning, how we can use planning, but planning can be slow. So we use the learning to make the controller real time. So now we have a policy that can be run in real time. And now I want to quickly also a bit talk about the adaptation part. So here is one, so let's say we learn the policy from optimal control, and now we have a policy that works in the real world, right? But there is a problem with this. Normally, these kind of policies are not super robust to the uncertainties in the environment, okay? Which means the contact uncertainty, when the contact happens, okay? And here, for instance, in the previous works in, I don't know, 3 or 4 years ago, we worked a bit on using RL on top of the learned policy, such that we make it robust to the environmental uncertainty. So simply what we did is that we have this policy that is learned from optimal control. Now what we do is that we start to randomize the contact in simulation and do RL to find a policy that is robust. And here, for instance, on the left, you can see that here is the first work we did on this. So here is the RL policy for jumping. And when you see we are changing, we are removing some the basically location of the blocks that the robot is jumping on top. And the robot is able to seamlessly keep its performance. And this is a very difficult thing to do in general in optimal control, because it's a optimal control problem with contact timing uncertainty, okay? And we also applied this to a quadruped robot, and we showed that actually we can learn different type of gait. That is very robust to different types of uncertainty. But the problem is that this is nice. We have a robust policy, but the domain randomization or contact randomization is a very ad hoc approach, procedure. Basically, you try to randomize things in simulation until you have the robustness that you want. And then I started asking question, can we formalize this with optimal control? Can we find a way to solve the uncertainty in the contact with optimal control? This is a very difficult problem. Why? Because the original optimal control problem is already a hybrid problem, which is very difficult to solve. Now, we are putting uncertainty in the switching surface of this hybrid system. So basically, now we are solving a stochastic hybrid optimal control problem, which is very difficult. So here, for instance, we have an optimal control problem, and the robot is changing its modes of contact, right, at a certain node. But the difficulty is that we do not know at which node it will switch, right? So this is contact timing uncertainty. And here, what we did is that we proposed to, rather than solving a stochastic hybrid optimal control problem, we cast the problem to a deterministic with a trick. And the trick was that we considered a switch. So we considered multiple nodes for the switch, and then we optimize for the switching time of the switching nodes, as well as for the uncertainty set that the system can be solved for this hybrid problem. Again, the idea is that we have a stochastic problem. We don't know how to solve it. We assume that we consider a certain duration of time that contact can happen rather than just one switching time. And we optimize for this time as a function of uncertainty and the environment, right? So this is the general idea. And actually, we saw that we could really make the system solve the optimal control problem very well, actually. So here is, for instance, jumping robot. So the environment, the height of the environment is changing after the jump. And if you look at our robust optimal control problem, the orange one, the impact can be maintained at a certain, amount. But if you use a nominal, let's say, optimal control, you can have different values of impact. And this is bad because basically you will break at some point in your robot. We also try to basically show how this is useful for manipulation. So this is a very simple example. So you have an object that is falling down, and the manipulator is trying to catch this ball, but the position of the ball is uncertain. Let's say the vision system that see the ball is uncertain. Basically, you have an uncertainty in the position, which means that you do not know when the contact happens. And then we let the ball falls down, and the manipulator should catch the ball. And basically, we want to minimize the impact of the system under this uncertainty. And the solution out of our approach is very interesting. Basically, if you look at the plots, so if you look at the position, so y position is the height of the end effector and the object. So the object is following a projectile path, right? Because it's unactuated. And the yellow and green, which are our approach, the strategy they take is very interesting. What they do is that they quickly go to very close to the position of the object with the end effector, and then they start going down, such that given this uncertainty, the impact of the system is minimized. Also, this is clear with the velocity case, right, on the right figure. What our approach does is that the velocity goes quickly to the velocity of the ball. So the robot goes close to the ball with the same velocity of the ball going down. And then this highly minimizes the impact forces, right? And here is, you can see in this figure what happens. The robot quickly goes to the position of the ball and goes slowly down, such that it catches the ball with the minimum impact force. Here is another example. So we have a pendulum. It's a like cart pole, or it's a cart pole basically. And the robot is pushed to the left, or the cart pole is pushed to the left, and it can make contact with the environment to recover, right? But the position of the ball is uncertain in this example. And here we have shown that, with our robust approach, we can have much more, cases that we can recover from compared to the non-robust approach. So here is a simple video of this thing. So first, with the nominal ball position, the nominal approach can work. But in the right, if you just make the position of the ball uncertain, so you can see that in the right, the pendulum falls down because it's encounters some basically discrepancy in the time, while the lowest one, which is the robust case, it can recover from, but use the ball with uncertain position to recover to the standing position. Okay. So this is one example of basically what I mean by adaptation. So to wrap up, basically, I showed you how we can plan for locomanipulation, cases, how we can plan for locomotion and manipulation using optimal control, how we can use learning to cache the solutions to a neural network that can be run at real time, and how we can take into account the uncertainty to design robust control for hybrid dynamical systems or contact-rich dynamical systems, right? In the future, we are working on this. We would like to again implement things for locomanipulation systems. So I already have this quadrupeds in my lab, and the humanoid will be added in October. So we have a full set of locomotion and manipulation systems, and again, we would like to make them fully autonomous. So the research I showed today was mostly the work of my lab here at TUM. And at the end, I just wanted to tell you that we have conference on robot learning in Munich this year, and actually the registration started today. So I think it's a very cool conference. So try to attend, I would say. That was it. Thank you very much.
Thank you. Thank you so much, Majid, for the great talk. You didn't explicitly talk about friction or how to handle friction and modeling the friction. And I think it's a very critical component of the whole thing. Could you say how we can tackle it when we were doing any kind of...
Here, if you look at the optimal control problem we are solving, right? The force limit you see at the bottom.
Yeah.
Includes friction cone constraints, right?
Okay.
So this is the continuous optimal control part of the problem. So this, I think nowadays we know to some extent how we can solve it. Still, it's not trivial. It's a very difficult optimization problem. But at some point, we now have enough knowledge about the problem. So we can solve this optimization problem. The only thing that is still difficult is to solve for both n, which is the contact sequence, and forces and the torques and positions. This is still, we don't know how to do it. That's why, I propose to use a combination of, Monte Carlo tree search and machine learning to find basically the discrete part of the atomical control.
I
But
see.
the continuous part, I think it's fine. I mean, it needs a lot of knowledge and work. But nowadays we have reliable solvers for this problem.
Okay. And
So
this would
normally
also
you can use off-the-shelf sequential quadratic programming solvers, right? Those
Yeah,
work
yeah.
really well for the continuous part.
Yeah. And this would also include like the full nonlinear friction cone, or you would have some kind of polygonal approximation.
I mean, you can do both. I think now we know how to handle also the quadratic constraints. So it's not
Yeah.
it's not a big deal nowadays.
Okay.
It's
Okay.
still, it was very difficult. I don't know, 5-10 years ago, still we didn't know how to handle it. But nowadays it's quite a standard, I would say.
And in terms of having this gap from simulation to reality, which I think still is sometimes problematic. What are your thoughts on that?
So this is a bit, so it depends if you look at so if you think about it through the optimal control lens or machine learning or reinforcement learning lens. Yeah. So in optimal control, sim to real is easier. And the reason is that basically we use the simulation environment and contact model mostly to test our controller. In reinforcement learning, so the thing is that building a simulation with contact is difficult, right? So none of the simulations work well in all circumstances with contact, okay? Because still it's a very difficult problem. So now if you use reinforcement learning, deep reinforcement learning, it means that you do trial and error in simulation. And if your contact model is wrong, which is wrong, okay, this reinforcement learning algorithm finds the best way to hack it. So it relies on the gradient of contact, okay? And this is bad. This is really bad. And normally sim to real becomes difficult, so you need to randomize. This is the way to solve it. You randomize the environment such that the policy cannot exploit the peculiarities in the simulation environment. Now you have a policy that works in the real. So sim to real for reinforcement learning is more difficult than optimal control, because optimal control, you do not let the optimizer to exploit the peculiarities of your modeling, okay?
Yeah.
But there is another point, the other point is that the whole idea of reinforcement learning from the beginning was to learn in the real world, not to learn in simulation and do sim to real. So it's deep reinforcement learning that has made people to do it. And the reason was that, it's very sample inefficient, that if you want to learn to walk on a real robot, you're going to break the robot before the robot learns to walk, okay? So sim to real for reinforcement learning is a new topic. It's not that it's been, again, a very old problem, right? It's at some point the attention of the field changed, because now you are learning in simulation and sim to real becomes a problem. But the whole goal was to actually solve it in the real world. So I don't know. To me, it's a fake problem, sim to real. It's not a real problem. It's a fake problem because it didn't exist in the beginning. Because of the deep learning, deep reinforcement learning, it started to appear in the literature.
Yeah. Okay.
Hi, Dr. Khadiv. I'm Ali. I'm a PhD student from KNTU. I had a question. My first question was about this specific slide. The physics equation that you are showing, I think it is very similar to the dynamics equation that you developed in one of your early works, dynamics modeling of a fully actuated humanoid with general robot environment interaction. Is it exactly the same, or it has some different types? For example, the binary term NE, I think that it was not explicitly in the model that you actually presented on your paper, or maybe I misunderstood that paper. Could you please say about this?
Yeah. No, that's true. So there, basically, in that paper, we said, okay, for different phases, we will have different dynamics, right? And here, N unifies all different dynamics, which means in different phases, with the use of N, you can switch between different modes. So N basically unifies the dynamics of the system in different phases. But actually nowadays so we really do not care about this equation anymore, because now there are very, very good software out there that can basically, so at the moment that I was working on the modeling and so on, there were not so many efficient dynamics, libraries available. But nowadays, you really do not need to think about this. Basically, if you use something called Pinocchio, for instance, is the rigid body dynamics library, it can solve the equations of physics of a whole humanoid in a fraction of millisecond. Okay, so nowadays, really, and it's a very nice solver with nice library with Python bindings. So in Python, if you want to find this equation, you provide a URDF, and then you just simply say, if you want to solve inverse dynamics, you say RNEA, just one line of code, and you have the full dynamics, right? So nowadays, you do not need to really develop the dynamics yourself, because there are very, very good libraries out there that you can use.
I got my answer. Thank you. And please, if you can you go to slide number 18?
Yeah.
Did you say that for this system, for the arm to grab the ball, in order to reduce the impact on the arm, it adjusts its speed with the ball? Am I correct?
Yeah.
I wanted to ask, so the control type that you implemented was position control. I wanted to ask whether if using impedance control was hard or maybe not necessary in order to lower this impact. What was the reason, for example, that impedance control wasn't implemented? Can it be implemented, or it's very costly?
No, that's a good question. So here I'm not talking about control. Here I'm talking about planning. Okay. So you want to find a plan, given that your environment or the ball is uncertain, what's the best plan that later you will track? So while you're tracking, you can do impedance control, you can do inverse dynamics, you can do whatever. It doesn't matter. So the plan is independent of the control at this point. So you have a system that you have information about uncertainty, right? So the ball is uncertain, and you know this. So you want to say, what kind of plan I can generate such that given this uncertainty and given all different scenarios that it can, that can happen in real world, I minimize the impact. And the strategy is very interesting. Why? Because the planning that is generated says that the ball is going down. You quickly go close to the ball and start moving down with the velocity of the ball, a bit slower than the velocity of the ball, such that at some point you will grab. This strategy is optimal in the sense that it reduces the impact for different things that can happen in real world. For sure, then when you want to track this motion, you can use impedance control that further make the basically strategy robust to the uncertainty. So these are two different phases. So here I'm only talking about trajectory generation under uncertainty, basically.
Thank you, Professor, for this talk. I'm very impressed. My question is about combining vision into the locomotion. So I want to ask your opinion about this, and I want to ask about, is it crucial to combine vision into locomotion, or is it very hard to model the vision side? So what are you thinking about this field?
So it depends, right? So if you want to plan on such an environment, like this very highly constrained environment, then vision becomes important, right? Here in this work that I showed, I assume that we have full knowledge about the environment, right? I didn't consider the perception side. But for for locomotion and on a flat terrain, I think vision is not necessary. It's you know, but if you are walking in a confined environment or constrained environment like this, vision becomes important. But I wouldn't say it's a big challenge because here, for instance, the main challenge is that how to plan, right? So here, for instance, what we did is that we said we assume we know fully the environment, we can plan, right? We know where the stepping stones are, and we can plan. And then what we can do is that we can learn directly in sensor space from the vision. And this is actually nowadays very popular, which is called, let's say, privileged learning, right? So what you do is that you do train, basically you plan in a privileged environment. Here, privileged environment or privileged set of information is knowing exactly where you have access to the segmented environment. And now what you do is that once you planned, now you have trajectories, feasible trajectories in simulation. And now what you can do is that you can directly learn in the space of the vision, either egocentric or you can use some, you know, some depth. First, you build the point cloud and, you know, use that. It doesn't matter really. So for sure, vision is important, but I wouldn't say it's a big challenge. That's my short answer.
Thank you.
Okay, thanks for the great talk. Yeah, this might be a conceptual question, and it's quite related to the discussion we just had. My question is, in your second point, like I think around second point, you said you replace the MPC module with imitation learning. Yes,
Yeah.
and that's all the works is after that, based on that. My question is, what's your strongest motivation to replace that part?
Yeah.
Because for me, I'm really looking forward to see how we can combine model-based method with other kind of learning methods. So for me, if you replace that, and then the model-based part seems to be gone already. So yeah, that's why I'm
That's a
asking
very
this
good
question.
question. Very good question. So here, my main motivation is that the nonlinear MPC, that if you want to, so the motivation to replace it is that MPC is highly computationally inefficient, okay?
Yes.
Because you need to run a very large optimization problem in runtime, and that's not a good idea. What I see as a, you know, the use of MPC is to basically guide the learning problem, you know. So at the end, so it's like, so conceptually, let's say you want to have a robot that walks in a flat environment, right? That's the only task that you have. What MPC does is that it's always planning, you know, into the future. But I mean, this skill, we know how to do it. So maybe we should stop planning. This is something that can be learned through a very small neural network. And then computationally, online computation goes to a minimum, right? So that's the main motivation behind doing this. I'm not saying it's the only approach, and I'm not saying it's the best approach. I'm saying this is the approach that makes sense to me. So there are other approaches, basically, to combine optimal control with dream. Actually, we recently submitted a review paper on basically learning-based legged locomotion. And in that review paper, I mainly explained, you know, what are the alternatives to this. So you can use reinforcement learning. So we explained 4 different ways that you can combine optimal control with machine learning. And here we only talked about using MPC as a policy search, okay? And then cache the solutions to a neural network. And for instance, this is not, again, a new idea, right? It has been there. For instance, you can look at the work guided policy search, and guided policy search is pretty much doing this, but for simpler problems. The other way to look at the problem is that you can say, okay, I want to keep the MPC, but what I can do is that I can learn some parts of the MPC, right? For instance, here, you can say, oh, I don't want to replace the MPC. I learned the contact planning part, the MCTS, right? And then I keep the MPC there. That's also okay, right? The only thing is that computationally, you need to do a lot in real time. So if you are fine, if your system can do computation, then you do not need to learn the MPC side. So you have a learn contact planning, part, and then you can run it with MPC. So this is another way to combine learning and optimal control. You only learn some parts of the whole pipeline, Again, these are not the only ways. For instance, again, I refer you to the survey paper, and then there we explained what are different ways that you can combine optimal control and machine learning.
Okay, thanks. I will definitely look into that. Okay.
Right.
All right. I think we can wrap up today because we already exceeded the time a bit, but it's fine. We're having very good discussions. I didn't want to stop it. Thank you so much, Majid, for the talk. Thank you for the time.